Thank you very much, Olivier, Antoine, for the invitation to present this work here for the symposium. So this is work done in collaboration with Antonio Picano, who is a postdoc in my group here at Collège de France, and with Giulio Biroli at École Normale. It's on archive and it will appear soon on physical review letters. So that's the outline. So I will present the type of question that we want to address and try to understand, which is thermalization in closed quantum many-body system. And we'll try to be introductory at the beginning to explain what is the question we are trying to understand. And I will try to convince you that to answer and understand this question, it's useful to look at the limit of infinite connectivity of a lattice problem and study this question using dynamical mean-field theory, which I will briefly summarize. I will then take an example, which is the Hubbard model, fermionic Hubbard model that is driven out of equilibrium due to some photoexcitation, and I will convince you that, in fact, we can understand where and how this Hubbard model thermalize at long times. And at the end, I will actually show you that the equation that describe this thermalization are in fact the very same equation that describe the propagation of traveling waves in unstable media. And these are equations due to Fisher and Kolmogorov, and I'll try to convince you that in fact there is a deep connection between these two phenomena. So very good. So what is the question we are after? What is thermalization in closed quantum system? We are interested about many-body quantum dynamics. So the typical setup we have in mind is an initial state, some initial condition, a wave function of psi 0, which is prepared, and we imagine to have a control of some system parameters, some coupling in the Hamiltonian, and we imagine to change this coupling in the Hamiltonian on some very fast time scale, and we will be interested in the dynamics that is induced by this very sudden perturbation on our system. You can think of this as some limit in which the variation in time happen on some time scale tau, and this time scale is the shortest time scale in your problem, so you can think of it as a sudden perturbation. And what we want to describe is that the dynamics after this perturbation is, we will assume that the system is isolated, decoupled from any environment, and evolves unitarily under the time-dependent Schrödinger many-body Schrödinger equation. And the question we would like to understand, and many people have been trying to understand in recent years, is in fact how the many-body system approach thermal equilibrium, and in particular how thermalization and the process of losing memory of the initial condition emerge under a unitary dynamics, and so how the system behaves at long times. So this type of question is, of course, in a certain sense, deeply theoretical. There is no such a thing as an isolated quantum system, and there is always some coupling to an environment. But in fact, from a different point of view, experimental point of view, we can make sense of this question as describing some interval of time during which the system is effectively decoupled from their environment. For example, if you think about a solid-state system and materials which are exposed to ultra-fast pulses, you can think of these pulses acting on femtosecond timescale, so essentially coupling to electronic degrees of freedom. And so if you probe your system on this timescale much earlier than the typical relaxation time between your electronic system and some phononic degrees of freedom, you can think of the system to be effectively isolated. Obviously, on longer time scale, coupling to the environment can become relevant, but on some intermediate time scale, this is a very good starting point. On the other hand, if you think about dynamics with artificial quantum matter, with quantum simulator, or with ultra-cold atoms in optical lattices, for example, you know that you can trap neutral atoms in lattices made by standing wave of light, and these are ideal isolated quantum system in the sense that there are no phonons, there are no impurities. The dynamics of the system is to a very good extent described by the unitary Schrödinger equation. And the systems are characterized by very low energy scale, very long time scale. And so they are the perfect lab where questions about the foundation of quantum statistical mechanics, such as, for example, how isolated system thermalizes, can be asked, and have been asked in the last decades or so. So thermalization, we can make sense of the fact that the system will reach thermal equilibrium very easily if we take a sort of semi-classical point of view, semi-classical perspective, and we think about Boltzmann, we think about Landau. There are quasi-particles in the system, they scatter, they interact, and the scattering allows to relax the initial condition and lose memory of the initial condition and redistribute energy. So this perspective is, of course, semi-classical and works in a number of cases. But in recent years, there has been the attempt to understand the emergence of thermalization and thermal equilibrium from a more quantum mechanical point of view in terms of what is called thermalization of eigenstates. So let me guide you through it. This is what is called the paradox of quantum thermalization. If you really think about this problem from the point of view of quantum mechanics, what do we have? We have an initial state. Imagine you have prepared your initial state psi 0, and you know that quantum mechanics is linear. You can always decompose this initial state in the eigenbasis of the Hamiltonian. So from the point of view of the eigenbasis of this Hamiltonian, the time evolution in unitary dynamics looks particularly boring, just a bunch of oscillation with the phases that are given by the level spacing between neighboring eigenvalues. So if you are interested, for example, in the dynamics of an observable OT, you can always write this as the sum over all the eigenstates of the Hamiltonian, some coefficient that encode the initial state written in the basis of the eigenstates. And so you see that if you take the long time limit now, you can invoke some sort of dephasing argument saying that energies, eigenstates which are off diagonally in a certain sense, so that such that this energy difference is finite, will dephase at long time. And so the system and any observable will relax a long time in what is called the diagonal ensemble, namely a mixture of states where only the diagonal matrix element survive. And so this argument should make you appreciate the paradox of quantum thermalization. In order for the system to thermalize, we would like this quantity on the right-hand side to describe some ensemble in statistical mechanics, depending on whether your energy is conserved, particle number is conserved, and so on and so forth. However, the coefficient Cn take memory of the initial condition because this coefficient describes the overlap of your initial state in the eigenbasis. And so it's not a priori obvious how you can, in fact, lose this memory of initial condition altogether, and how, for example, this diagonal ensemble can match the prediction of statistical mechanics, which only take into account the initial condition through global conserved quantities, for example, energy or particle number. So, for example, if you are in the microcanonical ensemble, you expect that quantum statistical mechanics tells you that the prediction for a local observable should be given by the average of this matrix element on the energy shell. And so these two objects look extremely different. And so to resolve this paradox, in the last, let's say, 2 decades, people have come out with what is called the eigenstate thermalization hypothesis, which is an hypothesis that comes from some of the field of random matrix theory and quantum chaos, which sort of postulate that if your system is sufficiently interacting, complex, and let's say non-ergodic, typical high energy excited states are thermal. What does it mean? It means that if you look in the middle of a many-body spectrum at finite energy density above the ground state, and you compute the expectation value of a local operator in that in that eigenstate, you will find the result that is essentially the prediction of statistical mechanics. And so if you take these ansatz, this eigenstate thermalization hypothesis, which is an ansatz on the matrix element of local operators, and you use some properties of this coefficient Cn of this diagonal ensemble, you immediately can deduce the fact that thermalization can happen. And so this eigenstate thermalization hypothesis was proposed in the 90s and had been in recent years rediscovered and put into a sort of test, numerical test, to try to understand whether it holds true or no, for which kind of system holds true or not. So what I will try to argue is that this approach to the question of thermalization is maybe good, but it's a bit abstract and does not leave us with a lot of understanding of what's going on. So I will try to propose and try to propose a different approach to this question, which is also, if you want, take inspiration more from the field of open quantum systems. So if a system thermalizes, if you expect that the system, when brought out of equilibrium, eventually left isolated, thermalize, reach thermal equilibrium, you expect that this system should be able to act as its own thermal bath. What does it mean? It means that if you take your system, you carve a little subsystem A in your system, and you look at the reduced density matrix of your subsystem A, well, then you expect that this reduced density matrix at long time will reach the Boltzmann distribution that you expect, for example, for systems that conserve, for which energy can fluctuate. So we would like to understand whether this picture is true, and we would like to make sense of this picture. But you immediately realize that this sort of open quantum system point of view is nevertheless a very unusual and unconventional type of open quantum system problem, because when you think about the thermal bath, you typically expect that the thermal bath is something that cannot be perturbed or essentially affected by your system. You think about a small system which is coupled to a macroscopically large thermal bath. This is clearly cannot do this job for us, because if a system has to thermalize, we want this thermal bath to adjust itself. Because the system, for example, you want that the initial perturbation is converted into some temperature, into some heating. So no matter which subsystem I pick, the rest should also be heated up by the perturbation. And so the kind of punchline of this talk is that the natural framework to think about this question is a framework of an open quantum system where your environment is adapting. And this should sound familiar for those of you that think about dynamical mean-field theory in this sense. So let me try to in fact show you that that this language is useful to understand this question, and let me try to show you what we have understood about thermalization using dynamical mean-field theory. So what is dynamical mean-field theory? Just one slide recap is you can think of it in many ways, but if you think of it as the limit of infinite lattice connectivity, this maps a lattice model that you have here on your left side, where, for example, you have particles, electrons hopping on a lattice, and this is mapped in the infinite connectivity limit into an impurity problem. This impurity problem describes a single site of this lattice, which is coupled to a bath that describes, on average, the rest of your system. And this bath is described by an hybridization function delta t minus t prime, which, very importantly, very crucially for what we will talk about today, if the system is globally in thermal equilibrium, is a function only of the difference between t and t prime. So the process of the particle hopping from the bath to the impurity and hopping out has a rate delta that depends only on the difference on t and t prime. So in order to solve dynamical mean-field theory, what you have to do, you have to solve an impurity problem in a given configuration of the bath and compute in particularly the Green's function of the impurity, because the self-consistent nature of DMFT tells you that the bath itself is given by the spectral properties of the impurity. So this framework has been developed and used to solve strongly correlated electrons and boson problems in equilibrium, and can also be extended to study dynamics, time evolution of, for example, of isolated system. So if you want to do that, and you think about the Hubbard model, for example, as an example, you can formulate this dynamics in the limit of infinite lattice connectivity. You will still map onto a quantum impurity problem. Here we use the language of Keldysh action, and so what this impurity problem will describe is again a single site which is coupled to a bath, but here crucially the bath of DMFT now is out of equilibrium. What does it mean that this bath is out of equilibrium? It means that the bath breaks time translation invariance. This delta, this hybridization function, depends on T and T prime. This again will have important consequences for what I'm gonna tell you. So to solve this DMFT, we have a number of tools, even though much less developed than the equilibrium counterpart. But what we have to do in principle, we have to solve a Dyson equation for DMFT with a self-energy that accounts for the interaction and the impurity physics. And in this talk, what we will do, and the results I'll show you, are based on iterative perturbation theory and weak coupling impurity solver, even though we think that the general picture holds more generally. And in addition, we will consider this DMFT to be implemented on a Bethe lattice, on a type of lattice that has no loops. And this gives a very simple self-consistency relation between the impurity Green's function and the hybridization, even though, again, we don't think this is a crucial point in this discussion. So using this framework, which has been developed and applied to a number of non-equilibrium problems, what I want to do, I want to study, for example, the dynamics of the Hubbard model. So we have electrons hopping on a lattice, we have local repulsion on each lattice site. We imagine an initial condition where the system is in equilibrium at some temperature T. We'll take units of energy to be the hopping, pH, and we'll take an interaction which is twice the hopping. And so the way we will couple the system, the way we will drive the system out of equilibrium is that for a very short period of time, we will couple the system to a bath, just for a very short period of time. This bath essentially does what you see in these three panels. You start from your spectral function in equilibrium of the Hubbard model. You will couple it with a bath that pumps essentially doublons in the upper band, even though you don't really see it for this weak correlation, that create excitation above the Fermi energy. And then after some short period of time, you disconnect the bath and you see how this excitation relaxes, and whether the system evolving unitarily without any external bath reach thermal equilibrium. So how do we see that thermalization is in fact captured by DMFT? This is something that is not new, but I want to first of all convince you or show you that this is true. DMFT is able to capture thermalization. You can see it in many ways. What I'm showing you here are two plots. The upper panel describes the distribution function. The distribution function of the electrons, which is essentially the ratio between two components of the Green's function, the Keldysh-Green function of the problem. You should think of this as a generalization of the Fermi distribution function. In fact, at initial time, you have some very sharp Fermi distribution that you see here with a green dashed line that describes the initial equilibrium state. Then the excitation arrives and the system evolves. And you see that as time progresses, the distribution function relaxes. And at long time, it reaches a very smooth, finite temperature, looking like Fermi distribution function, which matches perfectly what you would expect in thermal equilibrium at the effective temperature, the final effective temperature that you have generated by the non-equilibrium perturbation. So essentially, this tells us that DMFT equations are able to capture local thermalization, because if the system is in equilibrium, these two Green's functions are related by FDT, fluctuation distribution theorem, and this should be really the Fermi distribution. In the lower panel, we see that not only the distribution function thermalize, also the spectral function, so the retarded Green's function, the imaginary part of the retarded Green's function, also evolve in time, and a long time approach a value, a type of shape that match perfectly the equilibrium finite temperature result. Okay, so let me stress that the fact that DMFT, the thermalization is captured in DMFT, is not at all a novelty. People have seen that, even we have seen that before, for example, with Olivier a few years ago. And so this is well known. What I think was not understood is how this happened. And I will try to convince you that this, in fact, is not at all obvious. And there are quite some surprises in how this happened. Okay, so very good. So that's the precise question we want to ask. How does thermalization emerge in DMFT? So what does it mean? Well, we said that DMFT is a system coupled to a self-consistent bath. So if this thermalization emerges, it means that this thermalization emerges as a self-consistent process. In particular, we want to ask the following three questions. How does the system lose memory of the initial condition? How this happens? How the system heat up and convert the initial perturbation into a temperature? And most importantly, how all this is captured by an effective impurity problem. So I want to appreciate the fact that if you think about a conventional open quantum system coupled to a bath, you cannot have both. You cannot lose memory of initial condition and at the same time heat up the bath and heat up to finite temperature. What I will show you is that this can happen if the bath is self-consistent, so in DMFT, and I will show you that this happens in a sort of surprising way. Okay, so how do we address this question? We'll do something slightly different than what you typically would do with DMFT. So we want to look inside the self-consistency condition. What does it mean? So as this dynamics propagates, what we typically would do in a standard DMFT calculation is to enforce the self-consistency condition at each time step of the dynamics. So we typically would surf along the fully converged DMFT solution. Here we want to do something different. We want to iterate the DMFT equation step by step. And so what does it mean? We want to take an impurity, couple to a bath, solve for the impurity at that given bath, update the bath, and repeat this process. Okay? So to be very clear, as you see here in this box, we want to start with the initial condition at step n, impurity coupled to a bath, solve the impurity model, and compute the Green's function for all times in this given bath configuration, and then update the self-consistency. And so, which means this gives you a new bath, delta at step n plus 1, which is given by the Green's function at step n. This is what DMFT tells us. And now I'm going to show you the dynamics of this Hubbard model after photoexcitation in this sort of step-by-step DMFT procedure, and then I'll try to explain what that means. So what we have here, we have the dynamics of double occupancy, so the fraction of sites that are doubly occupied as a function of time, and DNT, the subscript n, tells you that this is a quantity which is updated step by step in this DMFT loop. So first thing first, let's look at the dark line, the thick dark line, which describes your usual conventional DMFT calculation. You see what? You see that the double occupancy shoot up at very short time. This pink region is where the non-equilibrium perturbation was acting, so there is some excitation, and then these doublons relax, and they reach a stationary state. There is this value over here, black thick line. Very good. So now we're going to see what happens in the DMFT procedure step by step. And so we plot here different iteration n equals 0, n equals 35, n equals 99. And what do you see? You see that essentially the dynamics stick to the DMFT solution up to some time, and then at some time scale, it deviates. And so we can identify two fixed points. There is one fixed point, which is the fully thermal fixed point, which is over here. And there is another fixed point that describes the memory of initial condition. This is the initial value of the double occupancy. And you see that no matter what, for a finite value of the DMFT iteration, you always go back to the initial state. However, as the iteration progresses, the time scale at which this second process happens moves and grows with n. So if I'm now going to plot the very same plot in a slightly different way, and you will see a sharp front. So what I'm doing here is what? I'm plotting on the y-axis the DMFT iteration, on the horizontal axis the time, physical time. So conventional DMFT calculation lies on top of this graph. We have converged DMFT on every time step, and we see what? We see that the system thermalizes immediately on some time scale. This is what we knew. However, if you see this plot at any finite time, you will see that there is a dynamics, that you reach the fully, if you want, thermalized DMFT solution, but then there is a front, and when you hit the front, you will go back to your initial condition. So there is a sharp front that separates the past from the future. And so this is how the self-consistent bath allow you to thermalize. The memory of the initial condition is always there. It's just that as you make your self-consistent solution more and more self-consistent, this memory initial condition is pushed away. So we can do the same game for other observables. For example, we can look at the dynamics of the total energy. And this is nice because, again, thick dark line is the full DMFT solution. You see that after the photoexcitation, the pink area, then the energy is conserved. However, again, if you play this game of looking at the iteration step by step and looking at the system as the self-consistent bath forms, you see that the energy is not at all conserved. You see that at finite n, there is always a time scale at which the energy leaks out from the system into the bath to cool off. And so again, if you plot this as a front, you see a very sharp front that separates heating. This red region describes heating due to non-equilibrium perturbation from the initial condition that remains at the initial temperature. Okay, very good. So we have established that there is a front, there is a wave, and thermalization happens in the DMFT as a wave that propagates. So I will try to convince you a little bit more, I'll give you a little bit more intuition why there is this front. We can understand why this front emerged. And to do that, I propose you to sort of run together this DMFT self-consistency. So imagine you start with your initial bath. Your initial bath is in equilibrium at some temperature. Very well. You do photoexcitation. You have now to solve an impurity problem which is coupled to this bath. No matter what you do, as long as this impurity is effectively coupled to the bath, so we can say as long as the Kondo effect happens, this impurity will thermalize with the bath at the temperature of the bath. The bath always wins. And this is something we know very well. Impurity models thermalize at the temperature of the bath. This means that any impurity operator becomes thermal after some time scale tau n, and also means that the local Green function of the impurity also becomes thermal after some time scale tau n. But now, if you go back and do the second step of the DMFT loop, what you have to solve is a very unusual impurity problem. You have an impurity problem where the bath, the hybridization function looks like this plot. You have a region in time where you have broken time translational invariant. You have an out of equilibrium bath. This is the Green function of the impurity at the previous iteration. But then after this time scale, eventually the system will go back to an equilibrium bath at temperature, in equilibrium with the bath at temperature at the initial temperature, and you restore time translational invariant. So the question is how this region evolves as you propagate this DMFT loop. And what happens, what we have understood that happens is that in fact the combination between the bath being out of equilibrium and the interaction on the impurity is the mechanism that gives you effective heating. So in this gray area that I showed you before, what will happen is that you will start to develop some effective quasi-time translation invariant domain, which describe heating. So this is, in fact, we have understood a long time ago with Aditi Mitra in a slightly different context. So out of equilibrium impurity problem with this type of bath can develop heating. And then the point is that once this breaking of time translation invariance is off, once the system restores time translation invariant, the impurity again will follow the bath. The only thing is that will follow with some delay. So the time scale at which the impurity follow the bath will be a little bit bigger than the time scale at which the bath has lost time translation invariance. As a result, you have a front. So we can look at this in real time. What I'm showing you here is the hybridization function of DMFT. So this is the bath, and we're going to look at the bath as the bath becomes self-consistent. Okay, so this is the first iteration. What do you see? You see a function of t and t prime, and you see this very characteristic symmetric form. This means that the function is a function of t minus t prime. You see, this line here is the function t equal to t prime. So the fact that you have a symmetry along this diagonal means that this function is time translation invariant, because this is the initial equilibrium bath. Now I'm going to run the DMFT equation. You will see the wave. You see that there is a wave that goes through the bath and make it thermal. I'll run it again. Oops, I'll run it again. So you see that, oops, you see that there is a wave that kind of swipes through the bath, makes it thermal, and goes away. So this is the thermalization front that I was showing. And the interesting fact is that if you see this correlation, you see also that as this wave goes through, the bath becomes, you see that the colored area becomes thinner, which means that the bath decays faster because the system has heat up, temperature is higher, and the correlation decays faster. So as you have this wave that goes through, time translation invariance is screwed, and you allow your impurity to thermalize. Very good. So I think I'm maybe, I don't know how much time do I have.
Well, yes, if you could conclude within a couple of minutes.
Okay, so I will just
3 to 5 minutes. Yeah.
Yeah.
Just 3 to 5 minutes. Yeah.
Yeah. I have just the last part. Now I want to convince you that in fact this phenomenon of thermalization as a traveling front has the same universal behavior of traveling waves in a stable media that are described by very well-known nonlinear equation, in particular the equation that goes under the name of Fischer-Kolmogorov Peskov. And so to do that, we will recast the DMFT in a slightly different language. We will first of all solve the impurity problem using what is called a quantum Boltzmann equation approach. I'll skip the detail, but I'll be happy to discuss. This is a sort of coarse-grained way to solve the impurity problem and sort of trade the very complex structure of the hybridization that I showed you before with a very simple and kind of transparent interpretation. We're gonna just parameterize this out of equilibrium bath with an effective temperature that depends on time. So this effective temperature, you can think of it as the slope of the distribution function that I showed you before. And so you see that this slope event evolves with time. So we're gonna take this effective temperature as our dynamical degrees of freedom. We're gonna solve DMFT with this quantum Boltzmann equation and show you, and this slide is supposed to show you that there is still the very same front that I showed you before emerge for the effective temperature as well. So you start from the initial temperature, you go to the final temperature, but you actually always keep a memory of the initial condition. Fair enough. But now the advantage is that in terms of this effective temperature, we can write down a very simple equation. We can cast the DMFT equation in terms of a very simple nonlinear equation. There is the FKPP equation that describes how an unstable solution propagates into a media. And so this is typically what you have. You have a dynamical equation that admits two fixed points, as you see here in the right-hand side. Y equals 0, y equals 1. These are two fixed points. One is stable, one is unstable. You ask how this unstable solution propagates through the medium, and this describes traveling waves. And so what we're going to do, we're going to rewrite the quantum Boltzmann equation of DMFT in terms of a Fisher-Kolmogorov equation. And this is the final result I'll show you here. It's just a parameterization. We'll just need to parameterize the Fermi distribution function in the right way. This variable u describes the sort of deviation from equilibrium. And then we will have a discrete version of FKPP where u is the dynamical variable. And you see that there is this coupling between n-1 and n, which is the key responsible for the front that comes from the DMFT self-consistency. And so why we do that? We do that because we can show that the DMFT data that we discussed and presented so far satisfy the FKPP scaling. They collapse once you use a traveling wave type of ansatz. You see what I'm plotting here is the effective temperature, but now as a function of n minus vt, so an ansatz that describes a traveling wave that moves at finite velocity. They all collapse, and this also allows us to obtain the scaling function of this front from the DMFT data. Very good. So maybe the last thing I want to say, there is in fact a physical interpretation that we can give to this parameter n, which so far has been mostly a conceptual tool to understand how the bath becomes self-consistent, but you can think of it as a sort of distance from the boundary in a Bethe lattice. I can tell you more if you are interested. Very good. I'll wrap it up. I'm sorry for being a little bit out of time. So I think we have understood something from merging sort of ideas from the DMFT with questions come from statistical mechanics. And the bottom line is that this DMFT approach is a very natural language to understand how isolated system can thermalize and can so act as a bath for themselves. And the surprising result is that this process behaves as a traveling wave, as a thermalization wave that falls in the same universality class of Fisher-Kolmogorov type of equation. And so this is, I think, the beginning of more investigation. In particular, we would like to understand whether this perspective can teach us something about situations in which thermalization failed to occur and ergodicity is broken, for example, Anderson on many body localization, or more generally, how this thermalization behave when the system is strongly interacting, strongly correlated, close, for example, to a Mott transition, or in presence of spatial fluctuation. And with this, I will close, and thank you very much for your attention.
Thank you very much, Marco, for the very nice talk. We now have, we're a bit late, but we still have a couple of minutes for questions. So please raise your hands. First question by Denis College. Hi, Denis.
Oh, hey, Olivier. Thanks, Marco, for the nice talk. Hey, I have a question which somehow bothered me in the last weeks, which is I'm wondering if this effect, this kind of what you call thermalization front propagation, it's a physical effect or it's a mathematical property of the underlying equations. So let me explain you. So what you're doing is essentially you're solving some nonlinear system of equations globally, yeah, and you use a particular solver. Yeah? In particular case, it's just like probably just forward iteration, right? Now let's say that we have been playing around and using different type of a solvers. So Newton's equation, any type of a nonlinear equations for nonlinear solvers for the nonlinear equations. And we see that this front strongly depends on the shape on the form of a solver which you use, right? And this
sorry, Dennis, just to clarify, solver, you don't mean impurity solver, you mean
no,
solver.
I don't mean the impurity solver. I really mean here, how am I solving a nonlinear equation system of equations which are the Cadron-Beim equation in the DMFT?
Just to clarify, thanks.
Good, thanks. So my question is, should I really understand this front as a physical property which is corresponding to some dynamics of systems around us? Or is this more of a mathematical property of the underlying equations? Do you have?
Well, I think it's the mathematical property that describes the physical phenomenon that is happening in DMFT, or if you want, is happening in an interacting system, which is subsystem thermalizing to thermal equilibrium and the rest becoming a bath. So from this point of view, I think if you take, let's say, a finite system, you could play the same game, and you could look at the carve a subsystem there, look at the dynamics of the subsystem, look into the bath, and ask yourself how this bath will become thermal a long time. And so the details might not be described by the very same type of equation, but in order for this bath to become thermal, there must be a mechanism that allows you to lose memory of the initial condition. So I think the fact that, but maybe I'll be happy to discuss, I think the fact that this front, this time scale for the front goes to diverge with n is a feature of a system that develops a self-consistent bath. And in fact, we know, we have already checked and seen that if your system is localized, this front does not develop. The system never lose memory of initial condition. So I think this is a feature of this problem. Then it's very like, so the pattern of traveling wave equation that you can have is very broad, and of course we don't know what is we don't know what type of traveling fronts you can have, and it might well be that if you change the way you solve, I mean, this is probably, there is probably an interesting interpretation of what this different way of solving means from the point of view of, you know, the perturbation converting into heat. I think, because if you think about, for example, the picture that you have in front of the screen, this process, you can think of it as the bath being attached to the boundary and going through the bulk, and this type with step n is the way this bath propagates into the bulk. So I guess if you do a different way to solve this nonlinear equation, you are sort of taking a weird path in this lattice. Maybe this makes sense. That would be very, I don't know.
That's exactly my problem. Yeah. What does this mean? Yeah. Okay, good.
I don't know. I don't know. I completely agree that this is.
Thanks. Next question by Walter Metzner.
Hi. Yeah, nice talk. Very, very nice extension of DMFT. So I was wondering about the extensions you had in mind, especially dynamical cluster approximation. So isn't it sort of almost clear that as long as you have a finite cluster, that qualitatively one would expect the same behavior? And so real questions arise only if you consider then the limit cluster going to infinity.
Yeah,
right?
Thank you. I think I agree, except that what is not clear to me is why, and this maybe is also related to previous question, why the front is ballistic. And so my question is whether if you include spatial fluctuation and you have a cluster that is a little bit bigger and you have interaction in this cluster, whether this front can be, for example, diffusive. This is not, so I was wondering whether this ballistic front depends from single side, comes from single side DMFT. But otherwise, I agree with you that the general feature should stay for a small cluster at least.
Yeah. And the limit cluster to infinity, I think it's clear that then it may very well depend on the system, because imagine that you apply this thing as an approximation to the Hubbard chain 1D, which is integrable, and that makes a difference, right, for thermalization. And on each level of approximation, finite cluster, the thing is probably not integrable, and then the integrability is probably captured just in the limit. And so from this, it's clear that this issue is then more subtle and will come with different cases. Right?
Yeah, I agree. This is a great point. The only thing that I can say is that even though Hubbard chain is integrable, it can still generalize, it can still thermalize to some generalized equilibrium. So I think there could be still a front between initial condition and an effective equilibrium, but it would not be a Gibbs equilibrium. But otherwise,
because of all these conservation laws.
Yeah, because of this conservation. Yeah.
Okay. Thank you.
Okay. Very good, thank you. We have more questions on here. Maybe then, if not, I can ask a very quick question. I mean, it's related to what has been asked before, but I mean, you've used a very specific impurities of, I mean, IPT. I mean, how does it change if you do something more sophisticated? Because also with an IPT, you could also try to compare with the GW calculation of the lattice. And so did you try other variants of the DMFT in this way?
No, we didn't. I can tell you that from the point of view of this traveling wave equation that is written here, you see clearly what will change. So this equation is nonlinear because of this functional phi. This functional phi accounts for nonlinearities, and in IPT, this is sort of just a simple polynomial of the Green's function. Yeah. You would have a more complicated and a priori unknown nonlinearities, but the coupling between n and n-1, this really comes from DMFT. And so I think that this is really what controls the fact that you have a front. But I think I agree that this needs to be checked.
Okay. Okay, thanks. Okay, we have time for very quick questions by Luca.
Yes. What sets the scale, the time scale at each step n?
So this is set essentially by the time scale that the impurity needs to thermalize to the bath. So this is typically either the coupling to the bath itself, or if you are deeply correlated, it can be essentially the Kondo scale of the impurity problem. Okay. Obviously, if this scale is 0, because you don't have Kondo effect, Olivier should tell me that I should stop, but we can talk more in Paris. It's